Hello, let me show you a Voxel engine, a little toy project that I've been working on and off for a few years. I haven't put any significant effort into it since 2018, but I've been thinking more about it recently. In 2018, I got a job as a professional graphics engineer, so it's going to be interesting to apply what I have learned since then. I originally started it in OpenGL 1, but it's evolved to an OpenGL 4.5 program, where the low-level rendering is done in C and the rest is in Lisp. Since it's mostly a renderer right now, it's mostly C. As you can see, the terrain populates in piece by piece, and there are separate metrics for renderer versus client. This engine has two threads. The renderer thread is pure C that manages the GPU memory and draw calls, and the client thread is mostly Lisp, split between two green threads, one for handling physics, input, and voxel updates, and the other for answering callbacks from the renderer. Currently, that is just terrain generation. The terrain generator is called by the renderer when it encounters an empty chunk. The callback green thread generates the chunk, then sends it to the renderer in the client, so the voxel memory is duplicated for thread safety. The client also has to message the renderer when a voxel is changed to maintain consistency. The view distance is reasonable, about 256 voxels, but the terrain is tiled. I was concerned about memory consumption. Each voxel takes up 16 bytes and the current play area is a 256 voxel wide cube, so that's 256 megabytes. That's silly when you realize that most of it is repeated air and stone. So, I was working on a compression algorithm before I took a break. It's a simple extension of techniques that were used back in the NES era, but the cool thing is that unlike LZW, random access of a voxel is constant time with new instructions. I want to finish that before I enable infinite terrain generation. The renderer is deferred, which is typically a little bit silly without many light sources, but I felt compelled to do that for SSAO. The program is heavily vertex bound, so doing a depth-only pass to prepare the SSAO texture for a forward render doesn't make much sense performance-wise. I also think that deferred is cool, even if it isn't necessarily as efficient as a forward plus renderer. I'll hopefully have more time for bells and whistles that utilize a deferred renderer to its fullest potential. That gets me to the shadows. It's a very simple 4K shadow map over a 128 voxel distance, hence the horrible pixelation. I could improve this with parallel split shadow maps, but I want perfectly crisp hard shadows. I could also do stenciled shadow volumes, but I'm thinking I'm going to try ray tracing the shadows. I'm currently not extruding the view frustum in the direction of the sun, so that's why this mountain shadow disappears when the mountain goes out of view. I have a few kinds of blocks coded up. The most dynamic is water, which flows from a source block. It flows too aggressively in every direction, but that's not bad for performance testing. In earlier implementations, this used to cause serious lag, but after some optimizations, it runs smooth as butter. There are also stairs and half slabs. All the blocks are rendered by sorting them by visibility and model shape, then rendering the blocks with instancing. One of the cool features I added was arbitrary 90-degree block rotations. This is accomplished with matrix lookup tables for rendering and a 24-state machine for performing rotations within the algebraic group. The first improvement I made after deciding to revisit this project is rather massive. It's the most significant improvement in performance since upgrading from GL Begin to VBOs. For some background information, the voxels are instanced, and the interior faces between two voxels are discarded. Before I revisited this, the interior faces were discarded with a geometry shader choosing not to omit the triangles. However, geometry shaders are rather slow and generally should be used as a last resort. A simple trick for triangle culling I learned is to set the position of the triangles outside clip space. Setting GL position x equals 2 and w equals 1 does the trick. The speedup was incredible, almost double the performance at lower resolutions. Now the interesting thing is that performance is not much worse if I were to disable triangle culling. It's almost imperceptible at low resolutions. It sounds reasonable that not rendering invisible sides should be a speedup, but unfortunately GPU microarchitecture stands in the way. I was originally doing this project on a Haswell CPU with an integrated GPU. Geometry shaders are much faster on Intel than AMD or NVIDIA, and the fill rate is significantly worse, making this a net win on Intel integrated GPUs and a net disaster on my discrete AMD card. Another reason why this isn't a big performance win on AMD is that the program is heavily vertex bound, and vertex culling doesn't do much to alleviate that. Groups of vertices, 64 in AMD, are packed into wavefronts and processed simultaneously. So if a voxel is surrounded on all sides but one, then 30 out of 36 of its vertices are masked out, do nothing, and still waste some resources. There were other problems going from integrated to discrete, particularly with my occlusion culling, which was a big win on a low latency system on chip, but required a rewrite for discrete cards, and it isn't that much of a win currently. The occlusion results have to be downloaded to the CPU during the frame, and thus have to pass through the PCIe bus on a discrete card. I'll look at it again when I have a better terrain generator with caves and other things more significant than some hills to occlude. I think that occlusion culling can be a big win with enough things to occlude. Games with a fixed layout levels have the opportunity to pre-compute a rough passive occlusion, such as through portal rendering like the middleware Doom 2016 uses, but that isn't available in a dynamic voxel engine. That goes to show the trickiness of GPU programming. What makes logical sense, the best O to the N algorithm, may not always win, and unfortunately there can be massive differences between different platforms. Unlike the CPU, the GPU is a black box we can only speculate about and only poke indirectly through drivers. There's more work I could do in performance, but now I'm fairly happy with it. I want to turn this into something a little more like a game with some of the features that I want. To that end, I have an 8-fold path to focus my efforts. I will be making a video series of these steps. Next up is voxel compression. I'll be going into some cool technical details about that and explaining how I achieve O-to-the-1 lookup. And that's all. I hope to see you next video.